Here we are using solar panel. After that, here we are using boost converter. So normally when you are going to connect panel directly to the load, so what will be happen? The load going to be changed, right? The resistance of that load also going to be changed because of changing load. So we cannot get maximum power from that panel because this PV panel like non-linear system. That means it depends upon two parameters. So one is temperature, another one is irradiation. So this irradiation temperatures normally depends upon environmental factor. Okay, so we cannot get a linear output from the solar panel. So we always get non-linear output. Okay, so in order to get maximum power for particular operating condition, that means a particular operating irradiation temperature, so we must go for a maximum power point tracking algorithm. So in order to operate, that means in order to apply maximum power point tracking algorithm, we need to use some converter in between load and then PV panel. So converter may be buck converter or boost converter or buck boost converter. So as per your requirement, but here we are using boost converter in between PV panel and load, and then this boost converter is controlled by means of this IGBT. When you turn on and turn off this IGBT, so you can transfer the power from this side to this side. Okay. So what's the use of boost converter here? The boost converter is used for matching the resistance of that PV panel with the load resistance. Okay. So for that purpose only, here we are using that boost converter. So in order to control that IGBT switch, so we need to implement MPPT algorithm. Okay, so here we are. I'm going to use two algorithm. One is INC, so another one is neural network MPPT algorithm in order to control the converter. Okay, so before that, I'm going to explain about PV panel. So here we are using 250 watts panel, uh, and then so 250 watts panel, and the maximum voltage at maximum power point is 30.7, and then current at maximum power point is 8.15. And also the parallel string here consider is 1, and then series string is 4. Okay, if series string is 4 means that means we have to multiply this 4 with the power. So finally we'll get nearly 1000 watts at the standard test condition. So standard test condition nothing but uh, standard irradiation and the standard temperature. So normally standard irradiation considered to be 1000 watts per meter square, and then standard temperatures to be considered as 25 degrees Celsius. And also we can see the PV IV characteristics of this PV panel. So we can choose this option, array at 25 degrees Celsius. So here I'm going to take temperature at 25 degrees Celsius, and then I'm going to make some uh, provide some different irradiation value. So here I given the irradiation value is 1000, 800, 600, 400. So by clicking this plot, right, so we will get a PVIV characteristics. So this is the PVIV characteristics of this consider PV panel array. So this is IV characteristics PV current and PV voltage, and then this is PV characteristics, PV power versus PV voltage. So you can see that it have some maximum power point. So this circle is considered to be maximum power point for different irradiation condition. Okay, so we can see the maximum power point. So here you can see that the maximum power for 1000 watts per meter square is equal to 1001 watts, right? For 800, the maximum power is around 799.6 watts. For 600, the maximum power is 598.5. For 400, it's around 395. Okay, so this is a maximum point for different irradiation condition. Okay, and also the maximum current at maximum power point also going to be changed. So you can check, this is 6.5 for 0.8, and then this point is 4.9. Current is 4.9 for that 600 watts per 600 watts per meter square, and then for 400 watts per meter square the current is 3.237. Okay, so this is the IVPV characteristics. So from that we can easily find out the maximum point for the different irradiation condition. Okay, so here the panel is considered as 1000 watts point. That means 250 into 4. 4 is model in the series. Okay. So in order to implement the MPPT algorithm, so we must measure two quantity. So one is PV voltage and then PV current. Okay, PV voltage and PV current, and it's going to be processed via incremental conductance as well as neural network MPPT. So this is incremental conductance MPPT. So here, so this is a code for that incremental conductance MPPT. Initially, so here we have to measure the voltage and current of the PV panel, and then so you can see that here we need to initialize the initial duty cycle is 0.42, and then maximum duty cycle is 0.85, and then minimum duty cycle is 0.1, and then change in duty cycle based upon condition is 0.00005. Okay, and next we have to initialize some parameter. So we have to take some global parameter, so like V volt, P volt, D volt, and I volt, right? So this is the PV panel voltage, power, duty cycle, and then current for the previous instant. So volt means is to be considered as a previous instant, and then the V and I going to be considered as a current instant voltage and current. Okay. So next the data type going to be considered as double. Okay, so all data type is going to be considered double, and then initially you have to check the value of V volt, whether the V volt has value or not. If that V volt does not have any value, so we have to assign the value. So the value here we are going to assign for the previous instant initially, so which is equal to 0. Here 0, I volt is 0, and then D volt equal going to be considered as initial duty cycle. Okay, initial duty cycle. So after that, after initialization of previous voltage, power, current, and duty cycle, so next you have to calculate the power by using this formula P equal to V into I, and we have to calculate change in voltage and change in power. So change in voltage, which is equal to current instant voltage minus previous instant voltage, and change in power, which is equal to current instant power minus previous instant power, and change in current, which is equal to current instant current and previous instant current. Okay. So after that, next condition in the incremental conductance method, here is we have to check the condition whether change in voltage which is equal to 0. So if it is equal to 0, no problem. So you have to maintain a D volt equal to, that means D equal to D volt. current duty cycle going to be maintained as the previous instant duty cycle. Okay, so no need to do anything. If suppose the dv is not equal to 0, next you have to check whether the change in current equal to 0 or not. If the change in current equal to 0, then we need to maintain the duty cycle as previous instant duty cycle. Or else if the dA is not equal to 0, then we comes here. Okay, next you have to check change in current whether it is greater than 0 or not. If it is greater than 0, we need to decrement the duty cycle by the amount of del T. Okay, in order to extract the maximum power from the PV panel. Or else if D is not equal to, not greater than 0, then we need to increment the duty cycle by the amount of del T. Okay, so this is the first step in that incremental conductance. That means first condition you have to check dv di. Okay, if suppose the dv is not equal to 0, we need to comes here, then mean we need to check the conductance of this change in conductance and the actual conductance. So whether it's both are equal or not. That means di by dv equal to minus I by. So if it is both are equal, then you have to maintain the duty cycle as previous duty cycle value, right? Or else if suppose both are not equal, you have to check di by dv is greater than minus I by v. The condition is true, so we need to decrement the duty cycle by the amount of del T. Or else you have to increment the duty cycle by the amount of del T in order to extract the maximum. So after doing everything, right, so next it comes here. Here we are going to check the duty cycle value. This is in between a maximum duty cycle and minimum duty cycle. Okay, because here we are mentioning the maximum and minimum. So maximum is 0.85, minimum is 0.1. The duty cycle value is in between these two ranges, right? Okay, if it is in between two ranges, no problem, you have to proceed as it is. If it is the value is not in between these two value, so you have to take the duty cycle current duty cycle as a previous instant duty cycle. Okay, so after that you have to replace the d volt, v volt, p volt and I volt with the current instant value. So this process will be repeated for the n number of samples. Okay, so this is a process of incremental conductance MPPT. So next one is neural network MPPT. So the neural network MPPT here based upon irradiation temperature, the neural network is trained by means of output voltage of the PV panel. Should always provide the max voltage at maximum power point based upon that irradiation temperature. Okay, and then you have to measure the actual PV voltage. So this PV voltage and the voltage in maximum point from the neural network will be compared here. So you will get the error. So that error going to be processed via PA controller. So the PA controller process this error signal and then it going to be provide the duty cycle for the next stage. Okay, so the output from the neural network and then INC. So the duty cycles here, the incremental conductance and the neural network MPPT going to be hybrid. That means I'm going to connect each other. That means hybrid both neural network and INC. So that's why here I'm going to use additional block. Okay, so I'm going to take the duty cycle from the INC and the duty cycle from that neural network, and then the final duty cycle is processed via PWM generator. So this is a PWM generator. So it will be generate the pulse for that IGBT. Okay, so based upon the duty cycle from that INC and then neural MPPT, it control the IGBT in order to extract the maximum power from that PV panel. Okay, so the first step in that designing of PV panel boost converter MPPT algorithm for the solar grid connected system. Okay, so next to process here. So this point, right, this is a load point, otherwise called this point known as a DC bias. So in DC bus, we need to maintain some voltage because it's going to be connected with the grid, right? So here we need to maintain some constant voltage. So here we are going to use another system, nothing but the energy storage system. So here I am going to consider uh, battery. So battery going to be used as an energy storage system, and then here I am going to use bidirectional DC-DC converter. So why we are using this bidirectional DC-DC converter? Because if the solar power having uh, maximum power, otherwise called the solar power having power is greater than load power. If, for example, you consider the load power is 600 watts, but PV panel have 1000 watts, right? That means the PV panel can supply a load, that means 600 watts load. The remaining 400 watts should be used effectively. That 400 watts going to be used for charge the battery. So during that time, what would be happen? So it going to be act as a buck converter. So here voltage is will maintain with at some voltage. For example, here we are going to maintain the voltage at 220 volt. Okay. If it is 220 volt, we need to step down the voltage. That mean, so this converter going to act the buck converter because this voltage battery is going to be considered as 12 star 6. Okay. Here I'm going to use 48 volt. Okay. 12 star 6 is 48. Okay, 48 volt. So if it is 48 volt, right? We must step down the voltage from 220 to 40. So for during that time, so it's going to be act as a buck converter. Okay. So next, this bidirectional can be act as a boost converter when the PV panel, that means PV power does not have any sufficient power to supply the load. Okay. For example, the load is 600 and then PV panel have only 400, but the 200 watts is needed for supplying that load, right? So during that time, the bat that means this bidirectional converter going back to here boost converter. So this 48 volt going to be stepped to 120. That mean it going to be, that mean the current direction of the battery going to be changed from the discharging mode, right? So it going the for the remaining 200 watts going to be supplied by means of this battery. Okay. So according with the power in the panel, right? uh, the battery condition would be changed. That means charging discharging mode. So PV panel have a rest power than the load power, then it battery going to act as in the charging mode condition. If PV panel power is less than the load power, during that time battery going to be discharged in order to supply the power. Okay. So here some simple voltage control here implemented. That means the DC link volt. That means this is DC bus voltage, right? This DC bus voltage is measured here. So the DC bus voltage and then is compared with the reference voltage. So here we are going to measure 220 volt at the DC bus. So the actual voltage is compared with the 220 and then is going to be processed by a PA controller. So the PA controller is next is processed by a PWM generator. So then PWM generator generate the pulse. So the bidirectional DC-DC converter has two switch, right? So here we are using inverting the pulse for these two switches, right? So from the pulse, the pulse will be inverted for this switch. So this pulse is directly given to this switch. Okay. So based upon load condition, the energy will be, again, powerful will be changed in the bidirectional DC-DC converter. Okay. So next process. So this is the working of this battery with the bidirectional DC-DC converter. Okay. Next, grid integration. So in order to integrate the system to the grid, right? So after the DC bus. Okay. So this is the DC bus. After DC bus, here we are using one single phase bridge inverter. Okay. After single bridge inverter, that means normally the voltage from the inverter is stepped wave. Okay, so should be changed to sinusoidal wave. So for that purpose, here we are using LC filter. Okay, so this LC filter used to have filter out the harmonic in that inverter output voltage, right? So here we are connecting some load. Okay, so load around 200 watts. Okay, and then here the load voltage VRM is going to be considered as 110 volt VRMS and then 50 hertz. Okay, and then here the grid voltage, right? The grid voltage will be considered as 110 volt VRMS and 50 hertz. So here I'm considering the 110 volt grid. Okay, single piece 110 volt grid system. So next we need to control this inverter according with the power supply from the solar and battery. Okay, so how much power we are going to supply to the grid? So for that here we are going to measure current, right? That means inverter current and inverter voltage. Okay, so here measuring these two things. Okay, based upon these two things we have to control the current flow from that solar and battery system to the grid. Okay, so initially we have to generate some here we are going to apply a DQ reference model. Okay, so here I'm going to consider reference current is 1, and then okay, reference current is 1, and then I'm going to generate the I reference sine and I reference cos. Okay, so in order to generate and sine cos, here we are using a PLL loop. So that means phase lock loop in order to generate that sine and cosine uh, parameter. That means that detail sine and cosine wave, right? So we need sine and cosine two parameter in order to generate TQ reference, right? So for that here by using VA grid voltage or inverter voltage, so we are generating that sine and cosine, right? So here you can see that this is input from that system. Okay, and then here we are using PLL. So finally we will get the sine cosine, right? So this model used for generating that sine and cosine wave. Okay, so the sine and cosine going to be used for doing that grid side control, right? So this sine cosine going to be generated based upon that inverter or grid voltage. Okay, so this will going to be used here, right? Here the I reference I'm going to consider 1 per unit, right? And then the sine cosine going to be is dmaxed by means of this dmax block. So first one is sine, second one cosine. So cosine going to be that mean this uh, CVO use only sinusoidal, right? Reference. That's why here I'm going to use 0, right? So I don't want to use that cosine waveform, right? So here you can see that one is multiplied with the sign, we will get the a reference. Otherwise why I am multiplying 0 means in single phase you have only phase current, right? Okay, so that's why I am using that only sine wave. The cosine wave I'm going to consider 0. So 0 means it's going to be considered as a neutral, right? Neutral current is 0, right? So after using that word AB and sine cosine, right? Here we are going to generate the DQ reference. That means how we are generating. So you can see that the first I reference is going to be multiplied with the sine. Okay, and then same reference going to be multiplied with the cosine, and then second reference going to be multiplied with the sine and cosine. Finally, we have to add this cosine with this sine and this sine with this cosine, right? So here we need to add in order to generate DQ D reference. So here we need to subtract in order to generate the Q reference. Okay. So finally we get a D reference Q reference. So next this T reference Q reference will be used during that current and voltage control. Okay. So here Here we are going to measure that IA, the IA from that inverter current, right? So it's going to be divided with the one current reference. So this current reference decide the how much current will be supplied from this solar PV and the battery system to the grid. Okay. So if we change this value, so we can change the current uh, supplying current from that solar PV system and battery system to the grid. Okay. So for that purpose only here we are dividing with this current reference, and then so here we are generating weekly reference. Weekly going to be considered 0. Okay, and this is going to be considered as a V reference. Okay, so so that means this is considered to be uh, phase A, and this is going to be considered phase B. So next you have to convert this AB to DQ. Okay, so this used for phase A and this used for phase B. So next you have to convert into AB to DQ. So already we see that right here like that. So same concept apply here. Okay. So this is actual, right? This is actual DQ value of that current IA. Okay. So this is a reference. The reference value of that 1 per unit current, right? So next process we have to compare. That means D reference going to be compared with this D, and the Q reference going to be compared with this Q, and then it's processed via controller, PA controller. So this is a controller, PA controller. So here we are going to compare that reference with the actual Q. So here we are comparing T reference with the T actual, and then it's processed via PA controller. So this PA controller going to provide reference voltage. Okay, that mean DQ voltage, DE and DU output control voltage, and then this DEQ going to be converted into actual ABC. Okay, by using DQ to ABC conversion. So this block used for converting that DQ to ABC. Okay, so after converting DQ to ABC, we have to use only that phase A component. Okay, phase B component. We don't use any phase B component to generate the pulse. Just you take only phase A component. This component going to be connected with here. So this is the control voltage. So here is processed via PWM generator, right? 4 pulse PWM generator, and then here I'm going to consider the frequency, carrier frequency is 7,500. Okay, so it will be generate the pulse. Okay, so the pulse going to be given to that so here we are generating 4 pulse based upon this control voltage. So this is going to be given to this inverter MOSFET. Okay, so it going to be control the current flow in the system. So this is overall circuit of the system. So next I'm going to fix the initially the irradiation going to be fixed 1000. Okay, and then current reference will be 1. Okay, here current reference will be 1. So you have to check the process. Okay, so I'm going to simulate this one. Yeah, so you can see that the inverter current will be nearly 1 amps. Okay, so you can see that the maximum power extraction from the PV panels around so you can zoom that one around 900 watts. Okay, because of that incremental conductance in the neural network MPPT. Then this is boost converter power. So this is PV current, then boost converter current, and then this is battery. Battery is current will be negative. So negative means the battery is in a discharge mode condition. So this is PV voltage, and then this is DC bus voltage. Okay. So now you can see that the state of charge of the battery is increasing. That means battery in charging mode condition. So because of this current reference one, so it's supplying nearly zero point 0.7 amps. Okay. So now I'm going to change this current value. Okay, you will get some. I'm going to increase the value to 2. Okay. So you can see the changes in the inverter current. That means the power. That means current from that inverter from solar and battery. Okay. When we increase, so you can see that the grid current going to be decrease somewhat because of the solar PV supplying the current to the system. So and also you can check that battery. So battery also that means because of the current reference change from 1 to 2, right? The discharging current, sorry, charging current going to be the decreases from -10 to nearly -8 times. Okay. Once again, I'm going to decrease the current here. Now you can see the variation. So because of decreasing current, what happened? The inverter current is decreasing, and also you can check that grid current is increasing, right? And here you can see that voltage maintained near around 110 volt RMS. Okay. So once again, I am decreasing current to 0.5. Okay. You can see that the current is decreasing. Here you can see that the current value is increasing, right? So this interaction between this solar PV and battery. Okay. Here the condition is I'm consider as 1000 uh, watts per meter square irradiation. So I'm not consider any change in irradiation condition. Okay. So this is the first condition. That means for constant irradiation and temperature. For constant irradiation temperature, we are testing the system with by changing the current reference of that grid inverter control, right? So next process, okay. Next condition I'm going to consider here. I'm going to make the current reference equal to 1. Okay. And then I'm going to make irradiation is variable, right? That means say every 0.3 second the irradiation will be changed from 1000, 500, 300. Okay. So if change in irradiation condition, what will be happen in the uh, power transfer to the grid and then charging of the battery. So we'll check that one. Yeah. So initially the guy used 1000 watts per meter square. Here you can see the power extraction of this PV panel. So after 0.3 second, the irradiation change from 1000 to 500. So we will check the changes in the PV power, boost converter power, and current, voltage. So here you can see that the DC bus voltage is maintained around 220 volt, right? So now the battery is charging mode, and also grid inverter has nearly 0.7 amps. Okay, because of current reference is maintained, the reference is fixed at 1, right? Now you can see that. So because of change in irradiation from 1000 watts per meter square to 500 watts per meter square, so you can see the variation in the power from the PV power and the converter power, everything. And also you can see that the grid that means DC bus voltage is maintained around only 220 volt. Okay, with the change in irradiation also. But you can see the battery current, right? So the current will be changed from -10 to uh, nearly 0, right? Battery is not in a charging mode or discharging mode, so it is in a ideal mode condition. So here also you can see the variation, right? It maintain constant here, not decreasing, not increasing, right? It maintain constant because of that means the PV power have enough enough power to supply to the grid or supply to the load. Okay, so next we will check after 0.3 second, no, zero point 0.6 or zero point 0.6 second, the irradiation change from 500 to 300, right? We will check the process. Okay, now we can see that after 0.6 seconds the irradiation change from 1000 to, sorry, 500 to 300. Because of that, the PV power also decreases because of decreasing radiation. Okay, and then you can see that the battery change from that means 0 amps current will be in positive direction. That means battery going to be in discharge mode, right? Because the power level in the PV is not enough to supply the load. So here you can see that the SOC is decreasing, right? Because the battery in discharging mode. But here you can see that, so there is no changes in the inverter current and the grid current. Okay, so here that load is maintained. That means load power is continuously supplying here, right? So this is the second condition of the operation of the system. Okay.